MOSFET configuration before, which had the basic 4 resistor configuration in common source circuits. So if you recall previously, the circuits somehow they look like this. So I emphasize on the fact that well you can have a source resistor RS as well, which tends to stabilize your Q point. I mean your VDSQ and IDSQ given their device parameter variations of Kn. So if you recall over here in this table, you see Kp for this for example was for PMOS, and you had this Kp parameter which was about 100 microamps per volt square in the example, and it has a variation of plus minus 5%. So this was microamps per volt square, and what we saw was that in plus minus 5% variation, the variation in VGSQ, IDQ, and VDSQ were less than 5%. Okay, I mean these variations as a, for designing of MOSFET as a common source circuit, RS tends to stabilize the Q point, so the variation is not much. Okay, so you see over here you have the RS in PMOS device. This is your PMOS device. Now the other way of stabilizing your circuit, MOSFET circuits, is to use a constant current source. Okay, so what you can do is to, instead of RS, you can use an ideal current source. Okay, and again, if your conduction parameter for NMOS device, let's say Kn, is varying, okay, there's a variation in Kn, you can still stabilize the device or the overall circuit. I mean the Q point in terms of IDQ and VDSQ are stable. Okay, if you are going to bias this with a constant current source. So this is your VDSQ. This is your Q point. Okay, the operating point of the transistor. Now consider the circuit. Okay, now the objective is to design a MOSFET circuit with a constant current source to meet the set of specifications which are indicated over here. Now the circuit configuration is to be designed as shown in figure 32A. This is your 32A. Okay, and this is the AC equivalent. This is the AC circuit which shows an AC source over here. Okay, there is a capacitor, a bypass capacitor over here as well. So this in B 32B you have the equivalent DC circuit. So in B you have the DC equivalent circuit. So this is an NMOS device. If you look at the direction of the current, it's out of the source. Okay, and so NMOS common source circuit is biased with a constant current source. You don't see a resistor over here. This is again for stabilization of the Q point, as we have talked before. So in the DC equivalent, you see that this is shorted out, and then your RG is also shorted out. So there's a short circuit over here, which means the potential at the gate VG is 0. Okay, so VG is 0. VG is 0, but VGS is not 0. Okay, VGS is VGS and VS. The relationship is it's related as minus VS. Okay, and then this is the difference over here is your VDSQ. Okay, VDSQ standard operating point. Okay, and the current through the drain resistor is the same as this current is from drain to source. Okay, and the conventional way of the conventional direction of the current. So IQ is the same current that flows in the resistor ID as well. Okay, so that's your the quiescent current or the Q point. Okay, quiescent component of the current, and then this is your VDSQ. So for designing of the circuit, now you consider this DC equivalent circuit, and the specifications are that design the circuit such that the quiescent point IDQ is 250 microamps. Okay, and VD is 2.5 volts. Okay, VD is 2.5 volts. This potential is 2.5 volts, and your gate potential is at 0 volts. So you can find you have to find the resistor RD over here. All right, from this considerations, and you see it's not hard to find. This is your VDD, so the difference of VDD and VD, 5 and 2.5 volts, that's a potential difference between these 2 points, divided by IQ, which is given as 250 microamps, will give you RD. Okay, so it's not very hard to find over here. And the choices are the transistor has a nominal values of threshold voltage as 0.8 volts, and this is your electrical conduction parameter of a transistor. It consists of mobility and the gate oxide. So this is 80 microamps volt square. Then the geometrical parameter ratio width to length of the channel is 3. That's available. But then there is a certain variation of Kn, plus minus 5%. And with this variation, we are going to see that how this current source IQ stabilizes your Q point, stabilizes IQ and VDSQ. So the idea is that this IQ is going to stabilize this overall circuit. Okay, so let's consider the DC analysis of the circuit as an example. We have the requirement is to have this. Let's keep that in mind that we need IDQ and VD as 250 microamps and 2.5 volts, and what is the RD and what are the parameters of the transistor. I mean the parameters of transistor are given, Kn, but how much does it stabilizes in terms of this variation? I mean, how much variation does VDSQ and IQ produce? Okay, so let's see. So the first thing is we start with the same assumption that either since your transistor is on, okay, so it's either in sat region or in non-sat region, and if you look at this equation, this parameter is your conduction parameter Kn, and then you have a quadratic. Okay, so VGS is non-zero. Okay, although VG is 0. So so let's assume the transistor is biased in sat region first. VDN is given as 0.8 volts. Okay, so that's fixed over here. So let's find out what VGS is. So Kn, I mean this Kn prime is 80 micro amps per volt squared, and W by L is 3. So you see you plug in those values over here, and ID is your drain to source current, that's 250 microamps. Okay, so that was specified over here. This is 250 microamps, and then you have your you need to evaluate what is VGS, and from this assuming the transistor is on and it is in saturation region, so we have started with an assumption. Okay, we are not sure if it is in sat or non-sat region, and for sat region we are considering this quadratic relationship of VGS and ID, because you see in saturation region there is no dependence of VDS on ID. So in the vertical axis you take your ID, and then on the horizontal axis you have VDS. So after the transistor, I mean this VDSQ point is passed beyond this, let's say the sat region. So this is VDS sat. Okay, this is VDS sat. So if VDSQ is greater than VDS sat, then you are in the saturation region. And in the saturation region, as you keep on increasing, so beyond this point, as you go on increasing, VDS ID does not changes. So you don't see the dependence of VDS on ID in this relationship. So we are assuming that to start with, we are in the saturation region. Okay. So solving this expression, well, we get VGS as 2.24 volts, and if you recall that VG is 0. So this also implies that VS is I mean this VS is minus 2.24 volts. Okay, basically that's the difference of VG and VS. So 0 minus VS is 2.24, so VS is minus 2.24 volts. Okay, so you can see it over here as well. Now that you have the VS, all right, the drain current can also be found out. I mean this ID is the same as IDQ, and this is 250 microamps. So VDD over here, this is clamped to 5 volts. This VDD is 5 volts, and we know what this VD is. VD is given as 2.5 volts. Okay, so VDD minus VD, the potential difference of these 2 points divided by the Houston current, gives you RD. Okay, and that comes out to be 10 kilo ohms. So again, the drain to source voltage, if you are interested to calculate that, just to check your, I mean, why we are calculating this is to check our assumption whether it is correct or not. So VDS, which is VD minus VS, 2.5 minus VS gives you 4.74 volts. And if you can take a guess, what is VDS SAT? Well, VDS SAT is VGS minus VDN. Okay, and VGS was 2.24 volts, and then you have so VGS, I mean VS is minus 2.24 volts, but VGS is 2.24 volts, which is the positive quantity. So 2.24 minus zero point 0.8 is about 1.44. So your since the drain to source voltage is greater than 1.44 volts, that means the assumption, our initial assumption, the transistor was biased in the saturation region is correct. Okay, so we are indeed somewhere in the saturation region. We are past beyond this point. Assumption that the transistor was in saturation region and there was no dependence on VDS was indeed correct. Okay, so that means this current is of saturation region, and we have the correct VGS. Okay, if not, well then we have to revert back and we have to take this IV relationship into the, I mean this IV relationship won't have worked, and we have to consider this biasing in the non-sat region. Okay, and then you will have the dependence on VDS, but that's not the case over here. Okay, so we have checked the assumption is correct. Now transistor is in the saturation region. So let's consider trade-offs now. So you see we have the RD, okay, and we have the VGS as well from the IV characteristics. So now what we do is we see that if Kn is going to change, the drain current remains constant. It remains almost constant. So you see the variation was in Kn, this conduction parameter over here. There was a variation in this Kn. So what happens is that you you involve this variation in Kn over here, okay, to see how much VGS changes and how much in turn VDS changes. Okay, VDS, I mean from VGS you are going to get VS, and then from this VS, well, it's going to affect your VDS as well. So let's see how much this quantity varies and how much does VGS varies for the given Kn. All right. I mean, in saturation region, we don't need to bother about ID. ID is not going to vary. It's constant. Okay. So once you have this for a given VGS, you have this you have defined the invariant layer. Okay. I mean, you have enhanced invariant layer. So there is no change with regards to VDS. But well, how much VGS changes will say how much ID is going to change indirectly. Okay. So in saturation, let's assume the drain source current remains constant. Then for Kn to vary from 76 to 84, you see previously we were considering this to be about 80 microamps. So now we are considering this deviation of 0.5, plus minus 5%. Okay. So with this variation, you see the variation in VGSQ it comes out to be about 2.209 to 2.281 volts, and the variation in VDS is about 4.7 to 4.781. Again, you see these are small variations. I mean, as percentage, VDSQ is 0.87% of nominal value. That is against a percentage variation of Kn. So this stability effect is one advantage of using a constant current biasing. Okay, so VDSQ just varies 0.87%, and ID in since VGS has a very small variation, drain current in the saturation region is not going to vary much, since there is not much variation in VGS. Okay, so your Q point is stable. I mean, the operation is not going to shift in non-sat, or there won't be any significant shifts. You're still in sat, and the drain current is still the same. So the comment is that biasing with a constant with the current sources tends to stabilize the MOSFET circuits against variation in the device or circuit parameters. Okay, so that's the idea. I mean, why we are biasing this with a current source that you must know is that you need to stabilize the circuit so that your operating point, Q point, is stable. Okay, and that's the idea. Now, if you recall, we have already talked of you see in a IC circuit consisting of CMOS and NMOS and PMOS technologies, we don't have the thin film or surface mounted resistors like this, which we use for the biasing as well. Before in the DC analysis, for the purpose of DC analysis, we don't have these physical resistors in the IC. Okay, what we have is these resistances R1, R2, RD, or RS. They're again MOSFETs. Okay, So we have a non-linear IV characteristics. We do have a non-linear IV characteristics for MOSFETs. I mean, this which we can model as a resistor. Okay, so the MOSFET device drain to VDS voltage can model uh, a non-linear resistance. Okay, given your transistor is all in saturation region. So that, how it well, let's consider a device which is commonly known as, and it could be N channel, it could be P channel. So let's first consider an N channel enhancement load device. This load means a resistor. Okay, so and this is a non-linear resistor giving the IV characteristics. So you see this enhancement MOSFET is connected in the configuration such as that shown in figure 34, and that can be used as a nonlinear resistor. So this is your figure 34 in which your gate is short circuited with the drain terminal. So VG and VD are equal over here. That means VG is equal to VD, okay, which in turn you can say that is equal to VDD. So VDD is the final controlling supply voltage that defines the potential at drain and at the gate, because your Vs in both VDS and VGS is set to 0. Okay, it's a common source circuit. It is set to 0. So the thing is, now if you have VDD which is greater than VDS sat, the transistor is always in saturation region. It supplies a constant ID current. Okay, so enhancement N-channel MOSFET for which VDD is greater than VDS sat, you have a constant. You have a constant ID current. Okay, so constant ID current, which is going to increase, which can be controlled again with VDD. Okay, so the idea is that the transistor with this connection is called an enhancement load device, or you can see this as a nonlinear resistor. All right. So since the transistor is in an enhancement mode, to turn this on, you know that I mean you need a certain gate to source supply, and that should be greater than threshold. Okay, so VDN for N channel is always a positive quantity. So for this circuit, you see VDS is equal to VGS. All right, because this VDS is D is G, so the drain potential is the gate potential, and then the source is common. So VDS is VDS sat. So actually VDS is VGS, which is which is also greater than VDS sat. Okay, and which is going to be dictated by VDD. So VDS sat is overdrive voltage difference of VGS and VTN, which means that the transistor is always biased in saturation region. So the general V characteristics, ID VDS characteristics can be written as such. I mean, you have this, there's no dependence of the current on VDS. So VGS is basically the same as, I mean, you can put it as this on the right hand side. You can substitute for VGS as VDS. But over here, what happens is that as your VDS is increasing, VDN is fixed, okay, given it's the device parameter, okay, threshold voltage of the device. Kn is the conduction parameter. Those parameters are fixed. You see that ID increases with VDS, okay, so there is a quadratic behavior of ID versus VDS. Transistor is on because VDS is greater than VDN, and it is still in saturation, but your current is now in this configuration. The current is now increasing with VDS quadratically. You see in figure 35, this is the current voltage relationship characteristic of enhancement load device, and this happens to be your VTN. So for example, over here, figure 35 plots the IV characteristic for this case, and Kn is set to 1. Okay, so let's forget about this parameter. This is normalized to unity. And your threshold is again 1. Okay, so that means when VDS is 1, well, there is no drain current. Okay, you are at the threshold, so ID is 0 over here. ID is 0. But as VDS is increasing, there's a quadratic or a square law which holds for the current, drain to source current. And you see that as the inverse of this gradient is your it shows delta ID, the rise in the current for the given VD, okay, and that is your resistance, okay. The inverse of this gradient basically models a nonlinear resistor, okay. So that is your forward-looking resistance R. So in ohms, okay. So if your VDS is greater than VDN, okay, which is the case. I mean, since VGS has to be greater than VDN, VDS and VGS is the same thing now. So once VGS is greater than VDN, the transistor conducts, okay, and with increasing VDS, or you can say VGS, there's an increase in the drain current. It's just like, I mean, you can visualize this as VG basically. You are increasing VG. So although the transistor is in the saturation region, it's like this. I mean, nominal and the normal characteristics of MOSFETs. Uh, there is no dependence on VDS. I mean, don't confuse that with the normal characteristics. I mean, we don't have this gate and the drain terminal short circuited connected to each other. So what is happening over here is, I mean, uh, also in this case, you see, this is for a certain VGS. Let's call this VGS 1. Okay, then you have VGS 2, then you have VGS 3. I mean, as you go on increasing, for an NMOS device, VGS has to be a positive quantity, anyways. So, and greater than threshold voltage. So, as you are increasing your VGS, you are also enhancing the channel, all right? So, there's more drain current. So, it's just like the same thing goes on over here. So, the VGS is changing. So, for each VGS, you have more and more drain current. Okay, so since VGS is short circuited VDS, VDS over here is your VGS. So as VGS increases, that means the drain to source voltage increases, or that means your VDD is increasing. So your current is also increasing. I mean, the space charge density of the channel is increasing. So your basically the current grows beyond the threshold point. This is VDN. Okay, so that's the idea. So you can use this configuration as a non-linear resistor. This is my non-linear resistor. I mean, I don't need to use a thin film resistances or surface mounted devices with MOSFETs and ICs. I can use a MOSFET as a resistor. Okay, MOSFET can be used as a resistor. You can use this as RD or RS. For example, over here, I mean, this topology is your load. Okay, this is your load. This is your RD load. And over here you have this again common source circuit. This is the driver circuit. Okay, and you are going to take the output voltage across the drain. Okay, so that's your RD. So that RD is also based on the MOSFET itself, but in a configuration that the gate is shorted with the drains, so that you have the nonlinear characteristic of IV like this. Okay, so that's I mean, with this ML transistor is your load transistor. This MD is your driver transistor. So ML is always in SAT region. ML is always in SAT. MD can be in SAT or non-SAT, and there is no uh, obligation over here. I mean, this depends on what is your input voltage V1, that defines the behavior of this transistor, as we're going to see in the DC analysis in the upcoming videos. So, well, this can be in SAT or non-SAT, the driver transistor MD. So, but over here, your the load current IDL and your VDSL have a non-linear current to voltage relationship, and you can model this as a non-linear resistor. I mean, this whole thing is a non-linear resistor. So, in enhancement load device, if an enhancement load device is connected in a circuit with another MOSFET in the configuration shown in 36, the circuit can be used as an amplifier or as an inverter in a digital logic circuit. So you see, in a digital logic circuit, you don't need resistors. Okay? You don't have this on the ICs. You don't have resistors. You have all MOSFETs. Everything is MOSFETs. So the load device ML is always biased in the saturation region. Okay, which is the case over here. We need this in SAT region, so that we can have this relationship of IV, okay, and VGS is VDS. So we are modeling this transistor by a load. So the transistor MD, called the driver transistor, can be biased in either saturation or non-saturation, depending on the value of the input voltage V1. Okay, so let's talk about this more in the next video. We can do a DC analysis of the circuit. Okay, so this circuit anyways shows the use of the enhancement load device with an NMOS driver. All right.